Hello. Right, okay, so welcome to Wave Motion, video 1. What an awesome vid. GIF, JPEG, I know what they're called. Right, okay, so the learning names of today's vid are to define the terms progressive, stationary, transverse, longitudinal, mechanical, and electromagnetic waves. I know that sounds like a lot, but actually most of them you probably know. And to know and apply the ideas of wave phase, wave equation, reflection, refraction, diffraction, and polarization. So, first thing we need to do is define the term progressive wave. And that is a wave which basically progresses, makes progress. Basically, the defining feature of it is that it transfers energy from point A to point B. So, yeah, as it says there, waves are caused by disturbances in a medium. So if I have a medium, which can basically be anything like, for example, this screen, I apply a disturbance, and it does a wiggly wave motion. So any disturbance which causes repetitive motion due to a force pushing it back and forth, like simple harmonic motion, which if you're in my second year you'll know about, if you're in my first year you won't know about, it's basically a restoring force, isn't it? Yep, so here I could generate a wave on a string by providing a perturbation, a disturbance in the string, and that disturbance travels along the string in the form of a wave or a pulse. That's progressive because the energy transferred from this bit to that bit. Or I could do it in the sort of back and forthy motion like that, and it translates again. And energy from this side to that side, not matter. I mean, in the case of this wave, some matter moves left and right, obviously, because that's the way that I'm doing it, but there's no net movement of matter, just energy. Okay, you can also define them as either mechanical or electromagnetic. Mechanical waves need a substance, a medium, a physical medium, we call it, in order to transmit. So that is water waves, sound waves, waves along a spiral coil or a rope, seismic waves, P waves, anything that needs such stuff to travel through. Electromagnetic doesn't need a substance, a physical substance. It travels through fields, the electric and magnetic fields. So it is about perturbations and vibrations in those fields. For example, gamma rays, X-rays, ultraviolet, etc., the ones on the list. They can also be transverse waves, which is the up and downy type, which has the definition waves in which the particles of the medium vibrate perpendicular to the direction of propagation. So your classic sine wave sort of shape, or longitudinal waves in which the particles vibrate in parallel to the direction of propagation. Like that. Well, you really didn't need to see me do that, did you? And there's some info there. So water waves, secondary seismic, and all electromagnetic waves are transverse, and longitudinal waves, sound waves, primary seismic. So like S and P waves in geography, which, yeah, is a real subject apparently. So there you go. I'm only joking, Karen. Yes, key terms. Right, so the first term. So if you look at a wave, you can represent any wave on a graph like this. Now it looks like a transverse wave, but really we're just talking about displacement on the x-axis and then some measure of change like time or distance on the y-axis. So this could just be compressing a wave, compressing a wave, stretching it out, compressing it again, and then stretching it out in the other direction. Or it could be just an actual copy of the movement that it would actually make. For example, my hand up, down, back up to the beginning, just like if I was whipping a rope or a skipping rope or a slave. You shouldn't have slaves. You know who I'm talking to. So yes, displacement. Why? This one here. So the displacement is the distance and direction of a vibrating particle in a wave from its undisturbed position. So it's basically how far up from there and in what direction. So positive is up, negative is down. It's how far up any particle in the system is being displaced during a wave cycle. Amplitude is the maximum value of displacement of a wave, which is these peaks here. or the troughs in magnitude only. And wavelength is the distance between two consecutive points that are what we call in phase, but you'll just know it as from the beginning of a wave to the end of a wave, or from a point on a wave to the point where it's doing and looks exactly the same. And I'll explain what phase is in a minute. I realise it's bad to use it, but that's physics. There's always going to be a bit of, ooh, we'll learn this at the end. So it's the distance between two consecutive crests or troughs is probably the way you know it from GCSE. But this consecutive points in phase is the one that you'll want to learn for the exam and how you want to understand wavelength in the future, because it's not always as straight laced as crests, troughs and stuff. So you might not necessarily have two identical points. I will explain that later. Period is the time taken to complete one full cycle to go past a fixed point effectively. Well, for a full wave to go past a fixed point, yeah. That's the way I'm going to say that. Frequency, 1 over the time period, or the number of full cycles that happen in 1 second. Yep, that's it, isn't it? Yep, so phase. Now, instead of me banging on about phase, which I just said I was going to bang on about, there's a video. So if you'd pause this and then look at the video by Brightstorm, it's life-changing. The guy is, honestly, just watch it. You'll understand what I'm on about. So pause this, watch that, rejoin me. So I'll wait. I'm back. Hi. See, I knew you'd find it funny. Right, okay, so wave phase. Wave phase. Yeah, wave phase. It's really important. It's weird as a concept, but not really if you've ever done the simple harmonic motion. That'd be fine for you. Okay, so wave speed. Speed at which a wave, signal, or any energy is transmitted from one point to another point. How fast will I detect this signal getting to that? That's wave speed. So if we consider a wave having wavelength lambda, period t, and frequency f, and moving with a speed v, then in time the wave will travel a distance lambda. So in a time t. That's just a defining feature that we've stated. So if we say that the wave speed is the distance travelled over that given time, we can say lambda over t is equal to the wave speed. And if you state, as we did previously, that frequency is related to time period by being 1 over that, then we can say this, and it leads to this equation, v equals f lambda, where wave speed is equal to the frequency times the wavelength. What you'll note there is any wave travelling through a medium has a fixed speed. Like light speed is the maximum speed. It won't be changed unless we change the medium. So sound has a speed that it does in air. I mean, it changes if the pressure of the air changes, but ultimately there's a speed of sound. Now, what that means is if you have a fixed frequency, that means you also have a fixed wavelength. That one means the other thing, or one defines the other thing, because the v is constant. So increase the frequency, decrease the wavelength. Increase the wavelength, decrease the frequency. Pretty obvious. It's pretty straight-laced stuff. Okay, so have a bash at this question. Determine the amplitude and wavelengths of waves A and B, shown in the diagram opposite, and then estimate the phase difference between those two waves at 0 centimeters from the source and at 10 centimeters from the source. And then comment on why do you think they are different. So if you'd have a little practice at that, and then bring in your ideas and answers to that to the session, that would be great. Equally, have a go at that. Pause the vid. Have a go. Bring in your answers. Okay, reflection. So, reflection's obvious. We all know it. It's like the most common thing in life, isn't it? It's how we all see. So basically, waves are sent at an angle to a straight reflector, or waves are sent straight to an angled reflector. Really just a reference point thought. Anyway, angle between the reflected wave fronts and the surface is constant, isn't it? So you've got an angle of incidence and angle of reflection. They're the same, you know that. It's just, you know it. I feel like it's stupid to say. You know what reflection is. Waves reflect. Refraction. This is really due to the slowing down of one wave in one medium when that disturbance then translates to another medium. So if the wave changes speed, then it will inevitably change its wavelength. The frequency won't be changed because the rate at which a disturbance is happening will stay the same, so it will change its effective wavelength, which will then change its pitch or change its angle as it enters another medium. Unless it's entering dead on, then it won't change its angle, but if it's entering at an angle, then it will change the angle that it's being pitched at. If it's entering a more optically dense medium, it will bend towards the normal. If it's entering a less optically dense medium, then it'll bend away from the normal. Please read. You'll sort of wonder why I'm on a video when I'm just asking you to read, but there you go. It's effectively I'm just explaining what I just said. Pause videos. That's the beauty of videos, isn't it? Refraction. We'll go into a lot more detail about refraction. You need to know some laws and stuff, but ultimately refraction, bending light due to optical density changes. Diffraction, this is where wave fronts spread out as they pass through a gap or go around an obstacle. So when the gap width d is very large compared to the wavelength lambda, so that's this one compared to that, the effect is very small, so the diffraction is not so great. As the gap width d is decreased, imagine it's sort of throttling a creature. You squeeze its neck and then its head gets bigger. It's like you make it, pinch it tight. I don't remember it like that. Think about it just because it's true. Effectively, the more close d gets to lambda, the more spread out the waves will be. And when d does hit lambda at the same value, that's the maximum point of diffraction. Ultimately, it's because the point where it behaves like just a point disturbance, as if you dropped a little rock into a pool. So it's like that repeatedly dropping a little rock into a pool. Each one of these waves, as it passes through that gap, looks like a little rock passing in a pool, hitting in the pool. You know what I'm saying. Right, simple as. Complete the homework questions attached to this video. It would be a cakewalk for all of you, I'm sure. It's not been difficult. Goodbye. I'm still here.